Hi everybody, welcome back. We've been talking about moment of inertia and the way that mass is distributed around a rotating object. And so in this example right here, we're going to be determining the moment of inertia of this grindstone and then using that to find the kinetic energy of the grindstone if we were to change the velocity. So, excuse me, we have a grindstone that is basically a cylinder, a rotating cylinder, and it has a radius of 0.610 meters. All right, and right away I'm going to know I need some more space right here, so I'm going to shrink this down a little bit like that. Okay. All right. So that's a radius, 0.610 meters. Let's go ahead and write that down. 0.610. All right. If the linear speed of the stone relative to the axe is 1.50 meters per second, all right? And by the way, relative to the axe, or it could be relative to the ground. I mean, we're assuming the axe is being held by a man who's standing on the ground. So think of the axe as being stationary, and the grindstone is what is actually moving. So the linear speed, that is the velocity, the linear velocity is 1.50 meters per second. And the stone's rotational kinetic energy is 13.0 joules. By the way, as I write this, I'm going to write that as simply a capital K with an R next to it. K for rotation. And we're going to contrast that against KL for linear kinetic energy, which we've talked about before. But KR is going to be rotational kinetic energy. That is 13.0 joules. Okay? 13.0 joules right there. Question is, what is the moment of inertia? All right. Again, that is like, it's like saying what's the mass of the stone, but it's like saying what's the rotational mass of the stone, or the way that mass is distributed around the stone right there. So this is a property of the stone that's not going to change. So we can actually use this in our next part, which we're going to have to do. All right. So part A right there is what is rotational kinetic energy? Or what is the moment of inertia? All right, I should have written that. That's A right there. I can't write next to it because, again, there's a right over here. There's a menu bar that I can't somehow seem to get rid of. Anyway, that's A. So let's find that out. You know, one thing that's mentioned or that's drawn on our diagram right here is our angular velocity, our omega, which we don't know. So it probably would be helpful to find that. So there's our moment of inertia right there. Let's find our omega. First of all, our angular velocity. Well, angular velocity is linear velocity divided by the radius, right? So that's going to be 1.50 meters per second divided by our radius, which is 0.610 meters. Like so. And so our angular velocity is going to be that fraction. What do we get? I get an angular velocity of 2.46 radians per second. All right, that's our angular velocity right there. Now I happen to know that we are going to need that, but it's always helpful to find, if you know this is one of your values right here, it's always helpful to find that even if you aren't given it, because chances are you'll need to use it, and I think we will. All right, so we want to know what the moment of inertia is. Well, we have an equation that relates a moment of inertia to rotational kinematics, and that is, rotational kinetic energy. Rotational kinetic energy equals 1/2 I times our omega squared, right? So if we want to solve for I, it's simply going to be that our I is going to be 2 times the rotational kinetic energy divided by our omega squared right there. All right, divided by our angular velocity squared. Well, we have all those values, and if we didn't, we certainly could have solved for this, which we did already. But that's our 2.46 radians per second. So let's just plug our values in and see what we get for the moment of inertia of this stone. By the way, if you hear any whining in the background, my black lab is sad about something. I don't know what, but she's griping downstairs, so try to ignore that. All right, well, 2 times, what is the kinetic energy, the rotational kinetic energy? That's 13 joules, right? 13.0 joules. And we're going to divide that by our angular velocity squared. So 2.46, that value squared is going to be in our denominator. And that is going to give us what? I get 4.30. That is our moment of inertia. And do you recall what the units are for it? Remember, moment of inertia is described as mass times radius squared, right? So that's going to be kilograms times meters squared. That's the unit for moment of inertia right there. All right? That's, you might say, our rotational analog of mass. It tells us how mass is distributed around this axis of rotation right there. All right, so that's a property of the stone that is not going to change. It's like saying we solve for the stone's mass, but it's a rotational mass. All right. Well, let's use that now to solve for part B, because part B is asking for what is now the new corresponding rotational kinetic energy of the grindstone if the linear velocity is 3.00 meters per second. All right, well, it's the same grindstone, right? So it's got the same radius. So the radius is still 0.610, is that right? Yeah, 610 meters. So that means our angular velocity is going to be linear velocity divided by the radius. It's going to be 3.00 meters per second divided by 0.610. All right? And I get that is an angular velocity of 4.92 radians per second. Okay? Why is that important? Well, because we have our equation for kinetic energy. Rotational kinetic energy equals 1/2 I times r omega squared. Right there. I'll just put the I in brackets. And remember, the I doesn't change. The moment of inertia doesn't change. So it's what we solve for right here. So we can plug that in for our moment of inertia of this grindstone. Let's just go ahead and do that and solve for our kinetic energy, or rotational kinetic energy. That's 1/2 times 4.30. That's our moment of inertia. Times our new angular velocity, which is 4.92. We're going to have to square that. All right. So now our new rotational kinetic energy is this. 1/2 times 4.30 times 4.92 squared. I get 52.0 joules. That's our new rotational kinetic energy. Now compare that to our first kinetic energy, which is right here, 13 joules. So we had half the velocity, 1.50 meters per second. So if we double the velocity down here to 3 meters per second, what happens to kinetic energy? It goes up by a factor of 4. Just like with linear kinematics, if you double your velocity, you quadruple your kinetic energy. The same thing is true with rotational kinematics. So we originally had 13 joules of rotational kinetic energy. Now we've got 52. That's a 4-fold increase. And that's all because we simply doubled the velocity. So I hope that helps to kind of link rotational kinematics to linear kinematics. That's it for example 10-12. Thanks for following along. Make sure you ask me if you have any questions, and I'll see you on the next one.